Hi everybody, and welcome back to Geology 311, Stratigraphy and Basin Analysis. This is the beginning of part 2 of the course, since we just finished our first exam. Part 2 is based strongly around the Brookfield text second part, Tracing Environments Through Space and Time. And we're going to be starting with Chapter 5, which is the vertical dimension. And in this lecture, we're going to be looking at local sections and quite a bit about the history of stratigraphy, which means we're going to be reviewing some of those concepts of lithostratigraphy, geochronology, chronostratigraphy, and so on. We'll be looking at breaks in the record and looking at how we divide local sections by type sections and contacts and formations. So let's jump right in. I'd like to start with the history of stratigraphy because I feel it's very important that we know where these concepts came from, and even sometimes including the ones that aren't really considered accurate anymore today. It's important to know where others made mistakes so we don't continue to make them. But the history of stratigraphy is really based on the idea that distinct layers of sediment that we call strata are deposited on top of one another, and based on superposition, the oldest at the bottom, the youngest at the top, over periods of time, whether it be thousands of years to millions of years, sometimes even more. And actually, this is a relatively new concept. The Greeks and the Romans recognized that our planet was ever-changing and what they called eternal, but they didn't put it into this kind of stratigraphic context. Once we had the fall of the Roman Empire and the rise of the Judeo-Christian Church, things really changed quite a lot. Everything was caused by a Genesis-style deluge. So everything was what we would say is an antediluvian explanation for all of geology. And that's because everything was kind of based around this biblical interpretation. Once we had the Renaissance and the Age of Reason, things began to move away from these kind of extreme supernatural views and more towards developed and tested scientific principles. One of the earliest important historical figures in the development of what we now call stratigraphy is actually Leonardo da Vinci. Da Vinci was one of the first to at least write down the idea, suggesting that rivers and streams carried fossil shells down from the Alps. And if they were in the Alps, they must be very old. So that was kind of an interesting concept. He viewed it as a mix of mud and fossils turned to stone and were then uplifted. And he illustrated this in one of his not so well-known illustrations known as a rocky ravine. Now, this is entirely wrong, but it's significant in that it shows a change in the way people were thinking about natural history and about the world around them. This, again, wasn't bringing in concepts like uniformitarianism, or let's see if this happens today, which it doesn't, but it was a change in thinking. And so we will give him a little bit of credit where it's due for that in and of itself. We also, of course, have to discuss a little bit more about Nicolas Steno, or also sometimes called Niels Stensen. Steno was the first to really suggest in print that rocks that are enclosing fossils had at one time been soft. So, in other words, he was one of the first people to start speculating about ideas regarding diagenesis and lithology. And what really convinced him, though, were shark's teeth. He noticed that sharks, when he would find dead sharks washed up on the beach, had teeth identical to these bizarre little structures found in rocks that some people called tongue stones. What these people originally thought was that these tongue stones were the petrified tongues of dragons and giant snakes. How they got a tongue out of a shark tooth, I have no idea. But luckily, Steno was the one to say, nope, these are shark's teeth. And today we see shark's teeth wash up on sandy shores and they get buried in sand. And now we have a rock that's very hard, made of sand, and it has a shark's tooth in it. It must have been soft at one time and it turned into stone. It was from there that he started really developing his ideas that we now call the laws of stratigraphy: superposition, lateral continuity, original horizontality, and of course cross-cutting relationships. So again, Steno's approach was a little bit different, but it really kind of set the stage for things to come as far as how we think about the geologic record. And of course, our examples of Steno's principles of superposition, original horizontality, lateral continuity, and cross-cutting relationships. What's interesting about all these concepts is they're based on observations and deductive logic. There's no fancy equipment that goes into it. The law of superposition is based on observations of modern environments and then applying those to what we see in the geologic record. The same with cross-cutting relationships, continuity, and horizontality. The Plutonists, such as James Hutton and Charles Lyell, also very important people in the history of stratigraphy and geology. Plutonists believed that all rock came from fiery volcanic sources. So igneous rocks are produced from volcanism, sedimentary from the erosion of igneous materials. Now, they're not entirely wrong, they're just not entirely accurate. We now know that sedimentary rocks can come from anything. And we also know that not all igneous rocks are formed from volcanics. Hutton is considered the father of geology. He's the first one to propose uniformitarianism, and this makes sense that Hutton would be a Plutonist, because Plutonists can't really see magmatic intrusions a mile underneath the ground. All they see when it comes to igneous rocks is volcanics. And so he sees volcanic activity, turns to stone, stone weathers, that's how we get sediments. So you can't really blame them for not knowing about something they had no way of knowing about. Lyell, though, took a very extreme view to defend Plutonism from this other form, which was called Neptunism, which is that all rocks are formed in the oceans. Of course, we know that lots of sedimentary rocks are formed in the oceans, but clearly not all of them. So both of these two individuals were starting to take an approach towards utilizing modern observations the best that they could. Actualism being a big part of this, understanding that uniformitarianism is really telling us that the natural laws and processes of physics and chemistry are uniform throughout time. Gradualism, of course, is another part of that. Usually, these things happen very slowly, but the rates of change can sometimes fluctuate. So while Hutton and Lyell were definitely on the right track, they didn't have a full scope and a full picture on which to base their claims. So again, we're not knocking them down for that. We're just recognizing where their limitations were. William Smith is an incredibly impressive individual from the late 1700s. Was one of the first to actually do biostratigraphy on a large scale, strata identified by organized fossils. He was an engineer, actually, and a surveyor. His main job was to survey where to put canals for the booming coal industry in England in the 1700s. So he would go around and look at exposed rocks and figure out where is their coal and how can we dig a canal to get our train cars close to this to get them onto barges. This really wasn't what he was interested in doing, though. He was very interested in developing a stratigraphic history of the British Isles. So what he would do is he'd get funding from his parent company to go do survey work, and his crew would be there for weeks doing all of this survey work, and he'd get on his horse and say, yeah, I'm going to go check out some areas a few miles away. I'll be on my own. I'll be fine. And he'd go and do his research, sometimes lowering himself down into abandoned mine shafts without anybody knowing he was doing this. He was one of the first, though, to realize that the distinct fossils that we find in rock units can help you link them in time. And so this is where the principle or law of fossil succession came from. And a big important part of this that we're going to get to further in a moment is the concept of extinction. Because seeing a fossil appear in the fossil record is great, in the stratigraphic record is great, but notice when it stops appearing, that's the extinction. That's when that organism or group of organisms, that population is no longer around. So he was pretty much the first one to start showing that you can divide the geologic record based on fossil content. And in 1815, he published the first detailed geologic map of England, intended for the development of canals and quarries and mines, as well as anything else people wanted to dig for. But he did run into a couple of problems. Notably, his work was stolen. He was sent to debtor's prison. His wife was in a mental institution. There were a whole bunch of things going on with William Smith. And I also want to point out in the lower right of the screen here, those are images of his watercolors that he would do of the fossils that he would find. So he was also an incredibly skilled artist, which you kind of had to be at the time because you couldn't take pictures or 3D laser scans. You had to draw everything you saw. And so he became an incredibly talented artist as well. If you would like to know more about William Smith, and I strongly encourage you to, especially while taking this course, I can't stress and recommend enough the book, The Map That Changed the World by Simon Winchester, who's also a really, really great historical author. In 1769, Smith wrote, quote, "Wonderful order and regularity with which nature has disposed of these singular productions," he was talking about fossils, "and assigned them to each its class and peculiar stratum." It's also a very poetic way of describing the importance of biostratigraphy. This is an image of the actual map Smith made, and it's big too. It's something like 18 to 20 feet tall. And if you look at a modern day geologic map of England, he wasn't that far off, and he did all of this on his own, by hand, over years, scraping together money and dodging his bosses so he could go do dedicated stratigraphic field work. We should all be aspired to do as such. Smith wasn't the only one, though, to use fossils in his description of stratigraphy. Georges Cuvier and Alexandre Bonnard of France did the same thing throughout the late 17, early 1800s. So they used fossil succession, but not in the same ways for correlation that Smith did. They were doing most of their work in the Paris Basin, which is pretty easy kind of pancake layered horizontal strata, but they described characteristics of the minerals and fossils and rocks, various shapes and colors and textures that they found within the Paris Basin into their seminal book, Géographie Minéralogique, which is still considered today to be a really great resource on kind of the early stages of stratigraphy. The different structures and colors and textures that they were describing to do. This is really what we call lithology today, isn't it? Where you look at a rock and you describe its mineral content, maybe its fossil content, the shapes of the grains, the colors and compositions and textures of that strata. That's lithology. We do that in order to put strata in their order, understand their lithology, and trace them across the basin. So they were really the first ones to start doing what we would now call modern-day lithologic descriptions in a stratigraphic context. And Cuvier was really the one to really push forth the idea of extinctions of past life forms. If you think about it, yeah, when before these guys were doing this work and before Smith was doing his work, nobody understood the concept of extinction. Pretty much if you saw a weird shape in a rock that looked like a weird animal, that animal was probably still alive somewhere, according to most of these people. But no, Cuvier was the one to really say that there's a turnover in life, and we can use that when we're studying rocks. So here's an example of one of their sketches of the Paris Basin. I'd like to go over the very odd and kind of strange case of Adam Sedgwick and Roderick Murchison. This is one of geology's most famous rivalries. And I can't tell you how troubling it is that it's not the only rivalry in the history of geology, but it's one of the bigger ones. But man, there's a lot of them. So let's look at Sedgwick and Murchison and their contributions and what happened. Sedgwick was a really well-respected and well-known geology professor. He was actually one of Charles Darwin's geology professors, and Darwin attributed Sedgwick as being the one who got him back interested in geology after he absolutely hated it for many, many years. Sedgwick is also noted for having named and described the Devonian system in England. Murchison was a friend of Sedgwick's, but wasn't a formal geologist by training. He was a very wealthy aristocrat who spent a lot of his days fox hunting, and then when he and Adam started hanging around, Murchison took up geology as a hobby, and he was a very intelligent guy, but he learned quite a lot from Sedgwick. So in 1834, Murchison is in northern Wales, and he discovers a geological formation that is sitting underneath, thus older than what they called the Old Red Sandstone of Devon, which is where the Devonian name comes from. So Murchison recognized, wow, I've got this new geologic formation, and it's right underneath Sedgwick's. I'm calling this the Silurian Formation, or this Silurian system, and he named it after the Silures, which is an ancient Welsh tribe. Okay, so far so good. Everything seems fine. However, in central Wales, Sedgwick found a formation that was even older than Murchison's, older than his Silurian unit, and he named it the Cambrian, after Cambria. Murchison was bothered by this because he felt that what Sedgwick had done was just take the lowermost portion of his Silurian formation and just gave it a new name and was kind of trying to steal his thunder. And they just went back and forth from there. So as you can see, Murchison was doing his work down in the south, Sedgwick more in central Wales. And at this point, they knew how to trace stratigraphy, but they just went back and forth, and really it ruined their friendship. They didn't speak again for years. They would bash each other in publications. It got really, really ugly to a point where, yeah, they absolutely stopped speaking to each other in person. It eventually got to a point where Murchison had used his wealth and aristocratic status to arrange for himself to be appointed to the head of the National Geological Survey of England, and then used his status there to have Sedgwick's name of Cambrian removed from all government books, texts, and maps. Pretty much saying Cambrian is no good, it's all just Silurian. And that was kind of the end of it. They did not speak for the rest of their lives. However, they were both wrong. In the end, those rocks were Ordovician, and they were both dead when that was discovered. And the reason for that is because of unconformities. Here's a cross-section across Wales. Yes, there's a Cambrian. Yes, there's a Silurian. What they were both looking at was Ordovician. And so the Ordovician was named decades later, when these two were already gone. I think the last correspondence I've heard of that was happened is, I believe it was Sedgwick's wife had passed away, and Murchison sent a telegram that just said, sorry for your loss. So they weren't totally heartless, but pretty damn close. So with that history kind of under our belt, let's really dive into more of the Brookfield text of Chapter 5 and look at the local section and look how we can take these historical concepts and apply them. One of the main focuses of Chapter 5, looking at the local section, is asking the question, how should the stratigraphic record be classified? Now, your initial thoughts might be, well, just base it on rock type. But there's a lot more to it than that, and since the goal of stratigraphy is to do more than just describe rocks, it's to understand and read the history of the Earth, we have to look at it from various perspectives. Can we break down the stratigraphic record by time? That may or may not link up with rock type. Rocks in and of themselves may not correlate with time. We have rock units that are what we call time transgressive. We can describe and break up and classify the stratigraphic record exclusively based on fossils with biostratigraphy, regardless of rock type. We can also do this with chemistry, looking at isotopic signatures and large-scale bulk chemical changes in the stratigraphic record. So in order to kind of break these apart and find ways of classifying them, we're going to look at three main stratigraphic classification areas. The first is lithostratigraphy, and when you're looking at just describing rocks, which is what lithostratigraphy is, you're essentially describing space. You're looking at the geometry of the rocks. We're not worried about time or biology in this case. It's just describing what kinds of rocks we have, how far they extend, how thick they are. That's what we mean by space, from like the literal sense of the word. Chronostratigraphic classifications involve relative time, which lithostratigraphy does not. So we have describing rocks in terms of space. Now this is describing rocks and stratigraphy in terms of relative time, relative order of events specifically. This does include biostratigraphy. This is looking at rocks in a time context, or time in a rock context. Okay, so we have lithostratigraphy, which is just describing rocks. Chronostratigraphy, which is describing time in the rock context. And then finally, we have our geochronology, which is absolute time, pure abstract time. In this case, it's the interpretation we get when we combine chronostratigraphic methods and lithostratigraphic methods. So chronostratigraphy is just absolute pure time. It would be like saying the Devonian period. Well, how do we know about the Devonian period? Well, because we have rocks and fossils that we can put into a context to tell us that during this interval of time, these are a bunch of events that happened that we have sedimentological evidence for, and paleontological evidence for, and chemical evidence for. And from that, we can interpret this unit of time, which is geochronologic. So we have rock units, and time rock units. Here we see table 5.1 from the Brookfield text, showing you just how we break down some of these different stratigraphic categories. Obviously, lithostratigraphy is really just kind of focusing on rock description. And so the basic stratigraphic terms we use for this are formation, which can be grouped into groups or broken down into members, which can further be broken down into beds. Biostratigraphy, of course, deals with fossil content in rocks, and we break this down into biozones, which can then further be subdivided into assemblage, range, acme, interval, and various other types of biozones. Chronostratigraphic and geochronologic units are commonly confused. You're not alone in that. The difference is chronostratigraphic units describe things like ionothems, erothems, system series stages, and chronozones. These are tangible descriptions of rock in a time context. So a body of rock unified by being formed all during a specific interval of time. Geochronologic units are the typical eon, era, period, epoch, age, and chron. These define abstract units of time. So for example, we know there was a Devonian period, but how do we know that interval of time existed? Because of all of the tangible evidence in the form of rocks and fossils and isotopes and so on that make up the Devonian system. So system corresponds to period. System is a collection of geologic materials that represent the abstract time of a period. I want to spend a little bit more time to really kind of get into the details of these breakdowns and subdivisions of the rock record. Lithostratigraphy, remember, is that study of the actual physical relationship of different rock units. We're not really worrying about time connotation other than relative superposition here. What's older is underneath and it gets progressively younger. Chronostratigraphy really is an integrated approach. In this case, we're looking at geologic units from lithostratigraphy, but putting them into a time context. So really it is time represented by geologic features, structures, and materials. So lithostratigraphy is just rocks. Chronostratigraphy is rocks in a time context. If we kind of expand chronostratigraphy a little bit more, we can also include how we get some of that information, which is biostratigraphy. In this case, we're looking at how the fossil record, especially faunal succession, and the concept of extinction, help us understand relative time in great detail in the geologic record. And a lot of this is done from correlating. We're correlating across large distances where certain organisms, remains are found in the geologic record that allow us to link those up to certain times. Magnetostratigraphy also offers a very detailed approach to understanding chronostratigraphic units and relationships. In this case, we're looking at the magnetic properties of rock. Now, most of the time this is done with igneous rocks. However, if you have sedimentary rocks that are enriched in iron, they can orient themselves, those grains can orient themselves prior to lithification and diagenesis to kind of reflect the Earth's polarity at the time. So magnetostratigraphy is pretty instantaneous and very, very detailed, while biostratigraphy is very detailed you're at the mercy of the stratigraphic range and chronological range of an organism, while magnetostratigraphy is rather instantaneous. We also have Alist Stratigraphy. If you break down that word, so like odd layering, in other words, this is looking at rock units that are defined by unconformities and other features that we get by what's called base level of change, which is something we're going to be getting into here pretty soon today. So Alist Stratigraphy is looking at rocks in a time context, utilizing in part by unconformities. And then finally, geochronology, in the sense that we are using it to determine an absolute time. And this is where we would be doing isotopic geochemistry, where we get pure abstract time. So this is what lithostratigraphy, biostratigraphy, magneto, and allostratigraphy combined give us a picture of an interval of time. All of these other things have happened in that interval, but geochronology is just the pure abstract time. Lithostratigraphy is what we deal with quite a lot, obviously, in this course, and it is defined as the study of the sequence and interpretation of layered rock sequences. This is based on physical characteristics, or in other words, the lithology of the rocks. We need these to, essentially it's a study of time, but it's not abstract time. It allows us to look at relative time, an order of events. Okay, so this image next is just kind of a random late Cretaceous to early Paleogene series from the Labrador Shelf, looking at the stratigraphy of these units, where we can see shales, we can see sandstones, and then we have a hiatus. That's the dark gray. So that's getting that allostratigraphy in there as well, along with the lithostratigraphy, collectively putting it into a geochronologic unit, as you can see from the ages and millions of years on the far left. Now, when we hear the word lithology, it has a couple of different uses. First, it can be used to describe the study and description of physical characteristics of rocks. That's what you do when you do your core sample description. It's what you do when you look at some of our facies exercises that we're going to be doing. This is what you do with hand samples and outcrops, and you investigate the lithology. However, we can also use this term as well to refer to the physical characteristics themselves. We can describe the lithology of a stratigraphic unit, like a sandstone or a shale. So we can use lithological descriptions, or we can use those descriptions to typify an entire unit itself. We can also divide rocks on the basis of lithology, and we do this in ways called the stratotype and the lithosome. A stratotype is really where we get the type section of a unit. This is where it is first described. So it's usually, a type unit is usually readily accessible, so it's easy to get to in a natural outcrop or possibly a mine or a borehole. This is the location upon which other units are compared to. So if you pick a geologic formation, which we'll talk to more about in a little bit, everywhere that extends is compared to the type locality where it was first described. So a stratotype is a formal designation. Now, a lithosome or lithosome, these are masses of rock with uniform character. Sloss in 1963 kind of described this as the dissolving away of all other rock types. This is more of an informal designation. So we can look at them in terms of lithology and compare them to, like, compared to a stratotype, or a lithosome would just be kind of bulk similarities and not a direct comparison to a stratotype. Now, with our lithostratigraphic units, here are some basic generalizations about these types of units. First of all, we're usually talking about sedimentary rocks. However, lithostratigraphy or lithostratigraphic units also include extrusive igneous rocks, so basalt flows or ash deposits. They also include metasedimentary and metavolcanic sediments and structures as well. So it is largely sedimentary, but it does include these other groups as well. Generally, our lithostratigraphic units conform to the law of superposition. There are exceptions, but generally speaking, superposition is kind of the default approach. They're usually layered or stratified and somewhat tabular in form. There are some areas where original horizontality, we have to, explain how rocks got stacked up a bit on an angle, but usually we're dealing with basic tabular stratified layering. We identify our lithostratigraphic units based on observable characteristics in the rocks, so the grain size, grain shape, chemistry, and so on. The boundaries between our units can also be thoroughly described, and it's something we'll be doing further in this lecture and next week as well. The boundaries between our lithostratigraphic units can be gradational, and in many cases they are, but they can also be very sharp, abrupt, and clear. So what do we use lithostratigraphy for? Well, what can it do for you? It can allow us to put our rocks in a geologic framework. It can help us establish relationships between stratigraphic units above and below the one we are investigating. And it helps with correlating to other lithologic units. It's important to note, though, the limitations of lithostratigraphy and that it cannot denote time for you. If you are standing in the Sundance Formation out in South Dakota, where you are in time depends on where you are standing from one end of the formation to the other, because formations are usually time transgressive. So you can't just say this formation is this many millions of years old. It largely depends on where you're at because of the time transgressive nature of lithostratigraphic units. Our units of lithostratigraphy are really based on assistive standardization. There is a international stratigraphic nomenclature code that we pretty much follow. And the fundamental unit of lithostratigraphy is the formation. A formation is defined as a lithologically distinct stratigraphic unit that is large enough in scale to be mapped at the surface and traceable in the subsurface. It may be just one lithosome or multiple, but it has traceable and mappable units above and below the unit in investigation. Okay. So all of our other formal lithostratigraphic units are based on the formation. If they are smaller than a formation, we call it a member, which is how we further subdivide those. Members are broken up then into beds. So it's the smallest formal lithostratigraphic unit. Or we can have a collection of formations into groups, where we have two or more adjacent formations that have some kind of unifying feature. Sometimes we call it a genetic relationship. And we can put groups into supergroups, such as the Newark Supergroup. I like to think of these as short and round, both in stature and in time formations. So, for example, the Newark Supergroup in New Jersey is a rift basin from the Triassic as the Atlantic Ocean was forming, as North America was rifting away from Europe. So it's a very dynamic collection of formations that all are related to this rifting event. So that's where we would get things like groups and supergroups. Members and beds really are what you're going to be describing in hand sample and in field exercise. You can go out again, let's say to the Sundance Formation in South Dakota, and you can describe the various members of that formation and getting down to how each bed within those members vary. So this is from a different text, but it's a really nice table that just kind of shows the hierarchy of lithostratigraphic units, where the supergroup is the biggest formal assemblage broken down into groups, which are broken down into formations. Again, the formation is the fundamental unit. So we either group formations or we break them down into members, lenses, tongues, beds, and flows. We'll get into some of these other types of lenses and contacts in a little bit. Now, as we move into looking at breaks in the stratigraphic record, we have to go back to some of Hutton's work, where he was the first to utilize those breaks to confirm some kind of cyclic view of Earth history. Really, now we know that unconformities are caused by relative changes in what we call the base level of erosion. Any kind of break in this record, any kind of change in base level of erosion, means that we have a non-conformable sequence, meaning we're missing sediment. If our rocks are representing time, occasionally you'll get a break where time goes on without any geologic record of deposition. Diastems are a form of a brief hiatus in deposition. Unconformities represent a hiatus that is more considerable in time. And of course, we have four main types of unconformities. We have the non-conformity, where we have exposed igneous or metamorphic, any kind of non-sedimentary rock that's exposed at the surface and then buried under horizontally bedded sediments. We have the angular unconformity, where the upper and lower strata are at different dip angles. So you had deposition horizontally, you had uplift, erosion, and further deposition. The disconformity, where we have sedimentary rock, it's eroded, and we deposit more sediment on top. And then the paraconformity, which is similar to a disconformity, except there is no erosional truncation. A paraconformity is very, very difficult to identify, and of course, it's the most common type of unconformity. Here we see figure 5.6 from the Brookfield text, where you can see a lot of these unconformities present. Over by the Front Range in the southwest of this, looking at the bedrock from Pennsylvanian rocks in Wyoming, you can see the Fountain Arcos on top of Precambrian basement rock. That would be a nonconformity. In the Hartville uplift, you have, well, in this case, you actually have both a a disconformity and an angular unconformity together, because the Hartville is sitting on top of the Guernsey, and that's an angular unconformity, but there's also erosional truncation. And then over in the Black Hills, you have a series, actually, of paraconformities. So we have all four present just along this unit here. Not to mention the fact that you're looking at Mississippian and Pennsylvanian rocks on top of Precambrian rocks. That in and of itself indicates a significant unconformity. Now, I want to talk a little more about these gaps, these diastems. We have two main kinds of diastems, and I've got references to some figures to look at in the textbook as well. First is a non-depositional diastem. This is going to be a gap in your stratigraphic record due to a minor break or hiatus in deposition. In other words, we're not eroding a lot, we're just not depositing much. So you have a skip in conformable deformation. Alternatively, we have the erosional diastem. This is a gap from a hiatus where there's erosion, so you've removed some of the original depositional material. So figures 5.7a and b and this ancient example in 5.8 show the different types of these non-erosional or erosional and non-depositional diastems. Now, the large scale, so figure 5.9 is also going to be showing you some large scale delta lobe switching. Minor unconformities, diastems, those are really hard to tell. But both of these types of diastems are caused by what we call base level of erosion and or aggradation. And this is because of fluctuations in environments. So here's figure 5.10 from your textbook, where you're seeing where we go from base level of erosion to aggradation. Notice that we remove material from the erosion side and it gets deposited at the aggradation side, and this is based on how sea level changes. Base level of erosion is when the lowest level at which a stream can erode through the channel that it's flowing through is generally equal to the prevailing global sea level. Okay, so this is like rivers typically aren't going to erode further down than base sea level. Base level of aggradation is the highest point at which that sediment can be deposited and built up somewhere else. Okay, so notice where sea level is and notice where base level is. our sea level, our base level of either aggradation or erosion are kind of at that same base level. We don't see erosion going down below the base level, and we don't see sedimentation going higher than that base level, and it is relative to sea level. It's not at sea level, it's relative to it. So you can have a shallow continental shelf. Storms will erode nearshore sediments, throws them offshore in these storm layers, but not higher up than where they were initially deposited. Now, to understand how unconformities and hiatuses and diastems work, let's look at barrel diagrams. This is a very simplified barrel diagram where you have time and you have a sedimentary record. So your sedimentary record in thicknesses of meters, so in other words, space is your y-axis and time is your x-axis. This shows the relationship between actual time and what's preserved and what isn't. Now you notice there's this curved line going through in between there. We have spaces for times 1, 2, 3, and 4. The base level will fluctuate up and down with things like changes in sea level. It'll change with climate, with storms, sedimentation rate, subsidence rates, and so on. So as base level fluctuates up and down, we have a curve that goes up and down. And on our up curve, we have sediment that's deposited. Now this could be permanent, it could be temporary. Sediment is eroded on the down curve. Okay, so our bold lines you see are where sediments are ultimately preserved. Our lighter up lines are sediment that's deposited and then later eroded, and the downsides are showing that level of erosion. Let's look at another example of a barrel diagram. Once again, we have time versus space, space being lithostratigraphy. Now we have three main lines here. We have this bold black line that we're calling A, and this is the overall change in base level. And this could be change in sea level. It could be a rate of subsidence, a change in sedimentation. Overall, this is the change we're observing. Now the other two lines, B and C, B being the heavy dotted line, C being the lighter dotted line, are changes that are going to fall of sea level based on climate or shorter term events like storms. Once again, we deposit sediment on the upside, on the downward curves, the downhill portions of the curve. If you're reading this from left to right, the downhill curves is when we're removing. So we have permanently preserved, temporarily preserved, and completely eroded. So this is a way that we can, especially if we add biostratigraphy to this, we can get an idea of how long an unconformity represents and whether we're seeing a significant main chunk removed or smaller pieces, depending on how base level was changing over time. Now, since we're talking about vertical changes and potential unconformities, we should also talk about contacts. Now, this is going to get into a little bit of lateral stuff, which is jumping ahead a week. I'm trying to hold back on that, though. We'll talk more about what's going on horizontally with changes more next week. But your contacts between lithology can come in a wide variety of ways. You can have separate units, or you can have a gradation within units. So these can be plane or a regular surface between two different rock types, and it's going to separate them. If they're conformable, you can see the incremental changes from one unit to the next. If they're unconformable, you are missing some portions of it. So notice we have in our laterally continuous units, we have a more coarse sand that grades into a sandy shale. Our upper portion, they're showing mostly a lot of grading. Our lower portions, where we have abrupt vertical contacts between a sandstone and a limestone, and then another sandstone once again. So this might indicate some unconformities. A conformable boundary is defined as any conformable strata that is unbroken from depositional sequences. So the layers are deposited pretty much continuously and uninterrupted. We can have abrupt or gradational boundaries in these conformities. You can have an abrupt change and it still be conformable. This could just be a sudden change in the characteristics of the lithology, and it's usually on the local scale. You can also have gradational conformable boundaries, as we're seeing in the upper portion, And this is because of long-term progressive gradual changes that we're seeing in that context. So for example, the sandstone becomes finer and finer up section until eventually we would classify it as a siltstone. We can also have what's called an intercalated contact, and that's what we're seeing in the uppermost portion of this diagram. This means we go from a shale and we end up in a coarse sandstone, but along the way we flip-flop back and forth with a lot of interbeds. And I don't want to get too much into these, but it's kind of hard to separate them out. You do also get laterally adjacent contacts, things like pinch-outs, what we call intertongues, and progressive lateral gradation, where we change from one kind to another. We're going to talk more about that next week, but it does play into this part as well. And that kind of concludes the information for Chapter 5 and for Week 4 of Stratigraphy and Basin Analysis. Just a couple of announcements I want to make before we sign off. First of all, there is no lab this week. I want you to focus on working on the remainder of Project 2, the second portion of that. Remember that all of Project 2 in one complete package is due Friday, March 5th in lab. So this is the entire Project 2, the Illinois Basin core description, the facies and geophysical analyses, and the write-up. I want you to also read through and print off Project 3 and bring it to lab on the 5th. This is a much shorter lab project than the previous one, but it deals with facies models and Walter's law. And finally, make sure that you read Chapter 6 of the Brookfield text and be prepared for our lecture next week on the horizontal dimension. So until then, we'll see you in lab. Have a good one.